Hi, kids. Hey, hi. All right. We're gonna talk a little bit about nuclear physics. Even though I'm not a chemistry teacher, I'm a physics teacher. It's all related. It's all good. So we're gonna talk a little bit about nuclear physics, and one of the things that we've been talking about in modern physics is how, like modern physics is kind of weird. We spent a bunch of the unit talking about how, hey, Isaac Newton thought that in the right around 1700, he thought that light was a particle, and he convinced the scientific community that light is a particle. And then around 1800, Thomas Young was like, no, look at this cool, demonstration with the double slits, and I get an interference pattern, and that could only happen if light was a wave. And so then for the next 100 years, scientists were like, hey, light is a wave. And then right around 1900, it was a little before that, Max Planck was asked to look at, light bulbs, and he figured out that, hey, you don't get all the same colors like you would if it was a wave model. You get red first, and then green, and then blue, and then he came up with this idea that, light comes in these quanta packets called photons. He didn't say photons, but he called them quanta, and the energy is based on the frequency, and it's kind of weird. And we're going to talk about something else that's a little bit weird with nuclear physics here. So let's talk about that. So imagine I have my Lego Wonder Woman. Isn't she beautiful? But imagine that I was to take her all apart. I'm not going to do that because it would make my kids mad. But imagine I was to take her all apart, and I was to measure the mass of all of the different pieces. Okay, and then I add all that mass up, and then I put her together, and I measure the mass. Well, we know, like with Legos, the mass of the individual pieces equals the mass of the whole thing, because, yeah, duh. But with a nucleus, that doesn't happen, okay? And that's what this video is going to be about. Like, what's going on? And that's it's called mass defect, and it's related to this famous Einstein equation, and that's what this video is going to be about. So, like, if we add the pieces up of a nucleus, so remember if this represents our nucleus, this is our model. I'm going to say the red ones are protons and the white ones are neutrons, just for the sake of argument here. This would be a carbon nucleus, a carbon-12 nucleus. Why? Because there's 6 protons, there's 6 neutrons, so total we have 12 nucleons, 12 things in the nucleus here. And then the atomic number is the number of protons, it would be 6, okay? But if you were to, and this is the weird part, so if I had individual things, so I was to measure the mass of a proton, we said this was a proton, and measure the mass of a neutron, we said this was a neutron, and add up 6 of these and 6 of these, it seems like I should get the mass of this. Now with golf balls you would, but with actual nucleuses, you don't. And that's what we're going to work through, okay? If you guys take a look on your College Board formula sheet, on the constant sheet here, they just tell you the mass of a proton and the mass of a neutron. They tell you, hey, look, the unified atomic mass unit and what that equals. But hopefully at this point we understand that a neutron is really made up of quarks, and protons are made up of quarks. A neutron, easy way to remember it, it's a dud. Remember, it has no charge because the down quark has negative 1/3 charge, the up quark has positive 2/3. So if you go negative 1/3, positive 2/3, you get nothing. Where a proton is 2 up quarks and a down quark. So if you go positive 2/3, minus 1/3, you get plus 1, and hey, that's what gives its charge. But, and I know I'm talking a bunch, but that's okay. But if you take a look, down quarks actually have a little bit more mass than an up quark, which is why your neutron is going to be a little more massive than a proton, okay? And if you look at this, and you can find this in your packet, it's, this page in your packet. This is this chart at the bottom that I put up here on the board. But you might be like, oh, wait a second. I have kilograms, which we know is mass. I have atomic mass units. Well, an atomic mass unit is just a smaller unit of mass. And if you look on your constant sheet, it says it right here that one atomic mass unit is 1.66 times 10 to the minus 27th kilograms. Why do they do that? Because that's really close to the mass of a proton and a neutron. So they say, hey, that's a useful mass. So they say this would be atomic mass units, just a different unit of mass. And then this one, and you might look at this one and go, wait a second. Mega electron volts over c squared? What the heck is happening here? Well, here's where that comes from, and just so you guys know it, this is on your formula sheet as well. You can see that, hey, one atomic mass unit is equal to 931 mega electron volts divided by c squared. Here's where that comes from. Okay? Energy equals mc squared. Well, that means m equals energy over c squared. Well, that means if I do one atomic mass unit, or unified atomic mass unit, that's going to equal 931 mega electron volts. Remember, mega 10 to the 6 million, so 10 to the 6 electron volts. Remember, electron volts, just a different unit of energy over the speed of light squared. So that's where it comes from, but you can measure mass. Energy is just another form, or mass is just another form of energy. Hopefully that makes sense. That's really what Einstein's famous equation is saying. But here's what we're going to do. Okay, you will need a calculator. And we are going to add up 6. Now, you have to decide, are you going to do it kilograms, or are you going to do it atomic mass units? We'll worry about this part in a little bit, but pick one or the other, and then you're going to pause the video, and I'm also going to pause the video, and we'll do the math. But you're going to pause the video, and if you decide you're going to do it in kilograms, do it in kilograms, that's fine. But you're going to take 6 times this number here. You're going to take 6 times this number here. Why are we doing that? Because we have a carbon-12 atom. And then we're going to have 6 electrons. Why are we doing that? Because we're going to say most atoms are neutral, which same number of protons and electrons. So you would take 6 times this number or 6 times this number, however you want to do it. And then you're going to add all that up. Okay? So get a calculator out. I'm going to pause. I'm going to stop the videos, and we'll do the rest of it in the next video. But get a calculator out. Do that. Add it all up, and then we'll talk from there. Okay? See you soon, kids. Bye.